Thanks, Bob, for inviting me to give a seminar here. Today, I'll show you some of my recent work on improving hurricane model physics with focus on the boundary layer scheme, the atmospheric boundary layer scheme using aircraft observations. So I'm going to discuss with you about covering these 4 questions. The first question is, why is the boundary layer process important in hurricanes, and what do we know about the mean structure of the hurricane boundary layer, and how to directly measure airship fluxes and boundary structure in hurricanes. And at the end, I'm going to briefly talk about how we use these observations to improve the model physics. So if you're not familiar with hurricanes, this is just a picture from a visible image, satellite visible image showing a typical hurricane. This with category 2 or 3 strength. And this, I believe, this Hurricane Irma. But if we do a cross section through the hurricane, then you see this is a schematic diagram shows the general structure of a storm. So for a strong storm, usually at the center of the storm, we call it the hurricane eye. The wind is actually pretty weak, even in the category 5 hurricane, I flew hurricane, so it's pretty calm. And the region with the strongest wind, we call it the eye wall. And also in the outer radii, we usually see some rim bands structures that would have convective activities. You see, it's like thunderstorms with clouds from the satellite images. And the hurricane is basically a natural great heat engine. You know, the storm intensity is supported by the energy through the ocean. So air interaction processes are very important for hurricane intensification and also maintenance of the intensity, because the hurricane is actually fueled through enthalpy fluxes, basically sensible heat fluxes, latent heat fluxes. Those are the energy for supporting the hurricane. And the surface friction, on the other hand, is like the brake in our car that reduce the strength of the storm. And also the energy is released through latent heating at upper levels in the eye wall region through condensation. And then low levels in the northern hemisphere, the flow rotates cyclonically, anti-clockwise. And near the top of the chopper, in the outflow region, actually the flow rotates cyclonically. So today I'm going to show you some of the structures of the storm at low levels, near the air-sea interface, kind of below 2 kilometers. Okay.
Hey, Jim, can you just tell us at what height the transition generally occurs from cyclonic to anticyclonic?
So usually like around above 10 kilometers. So the outflow layer is really located at about 14 to 15 kilometer altitude. So yeah. So this is a figure from the paper of Kerry Manuel's 1995 paper. Kerry Manuel is one of the famous professor, MIT professor. He actually relates the maximum hurricane intensity, the maximum potential intensity, to this very simple equation. So basically, for climate studies, people always use this equation in terms of the potential maximum intensity. So the Vmax is the hurricane intensity. The square of Vmax is actually proportional to the ratio of Ck over Cd. And Ck is the exchange coefficients for enthalpy transfer, and Cd is the drag coefficients. And here the T0 is the sea surface temperature. This is SST. And TS is sea surface temperature, sorry. T0 is actually the outflow temperature. So basically the temperature over here at the top of the outflow region. And then it also relates to the difference. K here is basically the enthalpy, is the temperature and the humidity part. And this is the enthalpy at the surface, and this is the enthalpy at the boundary layer. So basically, he used the Carnot engine theory, basically relates to potential maximum hurricane intensity to these processes. Basically, this equation also tells us that the importance of air-sea interaction. So basically, I mean, the CK and CD are related to surface fluxes. So that's the air-sea turbulent mixing process are important. Also, one important parameter is sea surface temperature, the SST. And also the difference in terms of the enthalpy between the sea surface and the boundary layer. This is very important. And also, so he used a very simple model, axiometric model, two-dimensional model, to derive these equations. And also, actually, in one of his papers in 1995, he pointed out that for a storm to develop in his model, this ratio has to be above 0.75. So this is a kind of theoretical-based estimates of this ratio. But actually, in one back to more than 10 years ago, so we try to measure these numbers through aircraft observations and to test his theory. So I'm going to show you some of the observational data later. Yeah.
So it's completely independent of size. You could have a tiny guy, or you could have, is there a maximum size that this breaks down?
This equation this equation has nothing to do with the size. This is a maximum potential intensity. So like for any storm, so like after 10 days, 20 days, what the maximum intensity would be. So this equation forecasts that. I mean, there's definitely limitations with this equation because it's axiometric model. So he also assumes gradient wind balance in this model. Actually, for instance, the boundary layer, the gradient wind balance may not work. So basically, I mean, based on this potential maximum intensity theory, it tells us the importance of the boundary layer processes. So this is a take-home message. I mentioned about the air-sea fluxes. Basically, these are the equations. If we want to directly measure these fluxes, we need to know the perturbations, the turbulent fluctuations. Usually, we can directly measure the fluxes using buoys, put an anemometer on top of the buoy, or we can use aircraft. So this requires really high temporal resolution data, usually 10 hertz or above. And in the models, in the boundary layer, because the model resolution is much larger than the scales of turbulent IDs. For instance, a global model, ECMWF, has a resolution of 30 kilometer resolution. And for HWRF, operational HWRF model has a gray spacing of 2 kilometers. So this 2 kilometer, even for the regional model, that wouldn't resolve the turbulent eddies, smaller than that. But the turbulent eddies can have scales as small as 10 meters. So that's why in numerical models, we need to parameterize these fluxes because the lack of the model resolution. So in the model, we have these mean variables. So we use coefficients, for instance, this eddy diffusivity, to link this flux to a mean state variable, so that in the model, in the momentum equation, we could actually parameterize these fluxes, and because those numbers are important because they are the key boundary conditions for the primitive equations. And for this is for the heat flux, this is for the humidity flux, and near the surface layer, at the surface layer is simpler than the boundary layer. Basically, we use the drag coefficients and the exchange coefficients for central heat and latent heat transfer. So the CH and CE usually they're equal each other, and equals the CK parameter here. So they're all equal in the models. So we try to use aircraft observations to estimate those numbers like CD and CK. I'm going to show you some results later. And I mentioned about air-sea interaction processes. Probably you are more familiar with this. This process happens not only in hurricane conditions, but also happens in non-hurricane. This type of boundary layer. I mean, like today. I mean, the many processes near the air interface affects the energy transfer, affects the momentum transfer, the central heat and latent heat transfer. For instance, we have this laminar circulation of the wave breaking, sea spray. We have all these type of processes, and in hurricanes, and all this process happens actually in the rotating environment, in the rotating vortex. So that makes it more complicated, than this type of boundary layer. And in terms of the atmospheric boundary layer, processes. I mentioned about the air-sea transfer, for instance, latent heat transfer over the ocean or the river. I mean, we have the sensible heat transfer that's due to the air temperature and land temperature differences. And we have turbulent mixing, the cloud and the boundary interaction, radiation, and so on. And this red line here shows the top of the atmospheric boundary layer. So usually we take the cloud base and in terms of the estimation, well, we usually use the mixed thermodynamic mixed layer depth. It's like ocean mixed layer depth. That's the boundary layer height. And usually in this type of conditions, in non-hurricane conditions, the boundary layer height determined by the wind profiles and the temperature profiles, they basically agree. I mean, they are the same. So, this is actually a boundary layer structure in the rotating boundary layer. This is a kind of the hurricane boundary dynamics. So I mentioned about the gradient imbalance. So above the boundary layer in hurricanes, usually within the gradient imbalance. So that's the balance between the pressure gradient. Where's the pressure gradient? The centrifugal force and the Coriolis force. So these three forces balance each other. But within the boundary layer, because of the surface friction, that's actually break down this balance. The friction reduces the tangential winds, and then that reduces centrifugal force, so that this pressure gradient, inward pressure gradient, becomes larger than the other two forces. That would induce the A gradient forcing. That A gradient forcing actually would induce a secondary circulation. So basically, as the flow rotates psychologically, that also the air also moves inward at the same time. So that's why we have this primary circulation, psychological circulation. At the same time, we also have this secondary circulation. So you have the inward, and by the air reach the eye wall, it will go up and then become the outflow. This is basically the outflow layer. I mean, within the boundary layer, so it's very interesting dynamics for hurricane boundary layer. So why is the boundary physics important in hurricane model forecasts and simulations? This is just an example from a research paper by Brown and Tell 2000. They run, it's the older version of the model, the MM5 model developed by NCAR. They run the simulation of Hurricane Bob 1991 using 4 different types of boundary layer schemes. So these schemes, the boundary schemes are basically similar to the schemes in the ocean models. I mean, we also have Miller-Yamada scheme, the K-profile scheme. So he tested 4 schemes. One is the MRF, is the medium range forecast model scheme. The Black Tar scheme. The Burke-Thompson is a kind of turbulent kinetic energy scheme, TK scheme, and a bulk scheme. You can see this simulated hurricane intensity in terms of both minimum sea level pressure and the maximum wind speed. They vary a lot. You see if you look at the wind speed, you see, I mean, compared to the best track, all these simulations produce stronger storms than the best track, and you can see the intensity can vary by 20 meters per second. I mean, like could be within 2 categories. So this type of study basically tells us, we need to understand the boundary layer processes, the physics, so that we could improve hurricane simulations in terms of intensity and structure. So from now, I'm going to show you some of my early work. We try to understand the boundary layer structure based on aircraft observations. So at the Hurricane Research Division, we routinely fly hurricanes. So during the hurricane season, we do aircraft observations. Actually, our base used to be at Tampa. So in the past 10 years, during summer, I always drive through here actually to Tampa to fly hurricanes. So in terms of the mean structure, here's the P3 aircraft. This is the relatively low altitude aircraft. We also have a G4. These aircraft usually we fly at about 10,000 feet, and we also have the G4 aircraft that fly at about near the top of the hurricane at around 15 kilometers. And this is the GPS drop sound. We usually drop it 10 to 30 of them in hurricanes. And this drop sounder measures three-dimensional wind velocities, temperature, humidity, and pressure. So usually when we flew into the eye of the storm, we drop one, then that gives the minimum central pressure. Excuse me. And then in the eye wall, we drop it so that we can get the wind speed. That would provide the estimation of the intensity. So the data will be transferred back to the National Hurricane Center. Actually, we will get the data within 6 minutes, and then we'll send the data to the Hurricane Center. Then they will know the storm intensity at that time. Oh, excuse me. So, in terms of the boundary structure, so back to, I have a paper published in Monthly Weather Review in 2011. So, since for each, I mentioned that for each flight, we usually drop 10 to 30 sounds due to the resources and the timing. So what I did is that I composite the drop sound data from multiple storms. So this is a database I looked at. So I composite the data. So I analyzed about 2,000 of GPS drop sound data from 13 storms, and I tried to group them together for the storms that with intensity larger than hurricane force storms. So basically, for any storms that has intensity greater than 64 knots, then I use the data. So I group the data and did a composite analysis and look at the axisymmetric boundary structure. So basically, I mentioned about the primary circulation, so the cyclonic flow, and also the secondary circulation. The left-hand side figure shows the tangential winds. That's basically the primary circulation. And this tangential wind speed as a function of altitude and radius normalized by the RMW, which is the radius of maximum wind speed. So when RMW equals 1, that means that's the eye wall region. So this is the strongest wind. You see this is the composites. This is kind of like composites of category 1 to 5 hurricanes. You can see the maximum tangential wind is about 50 to 60 meters per second, and that locates at about 700 meters out above the sea surface. And this is one way to represent the boundary layer height, the top of the boundary layer. To look at the height of the maximum tangential wind speed, it actually decreases with decreasing radius. And looking at the secondary circulation, this is a radial, the negative value shows the radial inflow, the air transfer from outside toward the storm center, and above the boundary layer is actually outflow. So you see the strongest inflow actually occurs at 150 meters above the sea surface. So it's very strong, it's up 20 meters per second. And this outflow is much weaker above the boundary layer, about 6 to 10 meters per second. And again, this you see that the inflow layer depth, the top of the inflow layer, this height scale also decreases with decreasing radius. And this, the maximum tangential wind speed is actually occurs within this inflow layer. So this is basically a climatology. This is how the boundary structure looks like, kinematically looks like in a typical hurricane. And this is another way to define the top of the boundary layer. To look at the thermodynamic mix layer. This is like in the ocean, you look at the temperature profile, you find the mix layer. I mean, in the atmospheric boundary layer, we use the virtual pressure temperature to try to find the mix layer depth. Basically, look at the difference between the vertical pressure temperature and the average value of the lowest 150 meter. So we see actually the thermodynamic mix layer is much shallower than the kinematic boundary layer I showed in the previous slide. So the thermodynamic mix layer is in the order of 300 to 400 meters. It also decreases toward the storm center. So this is kind of the change of this the boundary height with radius actually agrees with the scaling of the dynamical scaling. So this is a schematic diagram summarizing the boundary height scales. For instance, we have the inflow layer depth and the height of maximum wind speed. Those are the kinematic boundary heights, and this CI is the thermodynamic boundary heights. So the key finding from this study is that there's actually separation between kinematic and thermodynamic boundary layer heights. And this this is a RI. See, this is a critical retardance number method. Actually, between these observed high scales. I'm going back to this boundary layer in non-hurricane conditions. So as I mentioned, that the usually kinematic and the thermodynamic boundary high scale, they agree, but in hurricanes is a very different structure. So I mentioned about the GPS drop sound. So I want to show you a new type of drop sounds. So recently, back 2017, we actually put a infrared sensor at the bottom of this drop sound. So when the drop sound touches the sea surface, so that will give us measurements of sea surface temperature. So in this way, we can estimate the fluxes using a bulk relationship, know the exchange coefficients. So this is a Hurricane Edward, 2014. The upper figures show the visible image plus the flight tracks. So in Hurricane Edward, we actually did multiple aircraft missions. For instance, you see on the 15th, we have two P3. The 42, 43 are the P3 aircraft. We also have 49 is the G4 that fly at higher altitude. On the 16th, we have this AV6 is actually a Global Hawk. It's from NASA unmanned aircraft. It's a huge aircraft. This is a very expensive aircraft. That flew on top of the P3s. And then on the 17th, we actually did a unmanned aircraft. This is it's like a toy type of airplane. So we drop within the manned aircraft through the same hole at the drop. We drop this unmanned aircraft and let it fly within the hurricanes. So I can show you a picture. So then we validated the sea surface temperature measurements against the ASBTs. I think you must be familiar with this. ASBT is the ocean expandable that measures the ocean temperature profile and the salinity. So we drop the air sounds to be co-located with the ASBT so that we can calibrate and also evaluate the performance of these the SST measurements from the air sounds. And of course, the infrared measurements, they're affected by clouds. So we prove that the temperature measurements in the eye and in between the rim bands that worked better. So then I used the combination of the drop sounds, IR sounds, and the ASBT data to look at the air-sea structure and try to look at the boundary recovery problem. So this is an interesting observation. So this is the black line here shows the storm intensity of Hurricane Edward as a function of time at the dates. So you see from September 11th to 16th, the storm intensified and then weakened. So I look at two periods denoted by this purple lines, vertical purple lines. So on the September 15th, we had three aircraft measurements. We have good AR sounds and XBT data, and also the other period is on the September 16th. You can see that on the 15th, the storm was intensifying, and on the 16th, storm was weakening. But they have the same, basically similar storm intensity. So we want to look at how this air interaction processes or flux transfer would be related to this intensity change. So I composite the data, the drop sound, SBT data, to I can calculate the total enthalpy flux through the bulk methods. Basically, if I know wind speed, the air-sea contrast of temperature, humidity, I can calculate the fluxes. And you can see on the 15th, the fluxes are actually pretty large, in the order of 800 to 1,000 watts per meter square. But on the 16th, you see the fluxes are pretty small, because as the storm moves north over cold water, the fluxes are small. I mean, most of the cases are below 400 watts per meter square. And this middle panel here show the theta E. Theta E is basically the enthalpy. It is one way to represent the energy of a storm. And the shading is theta E, the shading color here. And the contour, the gray contours, actually from the Doppler radar observations, co-located with the drop sounds. The gray color shows the upward motion. So basically the draft, the huge clouds, deep convection. And this black line here, the contours are the downdrafts. So usually, this red curve with the shear direction is the environmental shear, the large scale shear Basically is the difference between the wind at 850 millibar and 200 millibar. So basically between the top of the boundary layer and the top of near the chopper post top. So this is so the shear usually like affects hurricane structure vertically. So when the shear is strong, then for instance, for a non-shear case, the vortex is vertical, but due to the wind shear, the vortex could be tilted. So the upper level, the vortex is tilted due to the shear. So that's actually induced the asymmetry of the boundary layer thermodynamic structure. So you see, usually on this upshear left quadrant, the theta is low, and on this downshear right quadrant, theta is high. That's correlated with the strong updraft because now energy to support the convection, support the clouds. And these bottom figures show this is a perturbation field. Basically, take out the mean at each radius. So this is wave number 1 components. That illustrates the asymmetry better. So you can see again on the upshear left quadrant you have low theta E, and downshear right quadrant have high theta E. So at the air parcel, the travels, because the hurricane is rotating fluid, so air travels along this inflow trajectory. So at the air parcel travels from the upshear left quadrant to downshear right quadrants, so the theta E is increased through air state fluxes. So air state flux with enthalpy flux of moistening the boundary layer and also increase the temperature so that the theta E would increase as the air parcel travels from here to there. And then, so interestingly, so I did a boundary recovery calculation. So actually on the 15th, I found that the enthalpy fluxes, they're large, they're enough to recover this theta E deficit from the upshear left to downshear right quadrants. But on the 16th, the fluxes are not enough to recover this theta E deficit. So basically, the take-home message is that the airstate fluxes actually are linked to the hurricane intensification rate. So basically, the intensifying or weakening, but for the energy, the theta E actually is more tied to the intensity itself. You see, I mean, when the storm have a category 4 strength, the theta E is comparable, but the fluxes are very different. So that this boundary recovery processes could be linked to the hurricane intensity change problem. So I'm showing you some of the mean structure of a hurricane boundary layer, and next I'm going to show you some of the observations in terms of the turbulence measurements. So I talked about the turbulent fluxes, the equation, basically the correlation between the turbulent fluctuations of the wind and temperature and humidity components. I'm going to show you how we measure them. So basically we have some specially designed instruments on the on P3 aircraft. We have this we call it the best aircraft turbulence probe, the BAT probe. We also have Rosemount gas probes, both installed in the nose and also fuselage. And also this box is actually the Leica hygrometer we put together. Actually, when I was a student, actually this instrument measures the humidity with 40 hertz, very fast response sensor, so that we can measure humidity flux. We also have the temperature sensors, and there's some pictures from the hurricane flights. Actually, you see Frank Marks. This is probably my first hurricane flights, and you see we are very happy after flying hurricanes. this is after hurricane missions. But anyway, so we did some very brave. Actually, this is a storm back to 2003. I told Dennis, Bob, some of the stories of the flight. Actually, this is a P3 mission in Hurricane Isabel 2003. This is a weather image. You can at that time we did a boundary layer experiment. This is the aircraft altitude. You can see the usually during the ferry time, the aircraft flying at around 4 kilometers altitude, and then after we circle in that eye, actually the P3 was flown into this outer core region at about 100 kilometers away from the center. So we did a step descent. So basically, you can see we descended this airplane down to 60 meters. Actually, this is a Category 5 hurricane. So we actually did some test flight in other storms, but these data are the best data we got. Actually, I was lucky. I analyzed the data during my PhD work. The sensor we put worked actually. so you're lucky. You can see this is the planned. This is the stabilized experiment. This is the proposed module. Usually before our aircraft missions, we already have a field work plan, like as you do to deploy buoys here. So this is actually proposed track, and this is the real track. This is the aircraft altitude. You see the P3 was flown at about 400 meters, and then down to 300, 200, and then as low as 60 meters. So the flight level winds is actually about 40 to 50 meters per second. So using this data, this is actually, this picture, the background picture was taken by one of the scientists on the aircraft when the aircraft was at 200 meter altitude. So you see the waves and a lot of sea spray, wave breaking. This is a real picture. And this is another picture. This actually, we did a dual aircraft mission. So during stabilized, the 42 is flying on top of 43. This was taken by the scientist on 42 for 43. This is within the boundary layer, and then this is this is kind of the probably further away from the hurricane. They take this picture. Oh, this is some data. The aircraft data. You see, this is from the lag at 70 meters. And we try to fly at a constant altitude so that for flux observations, this is the aircraft pitch, roll, and heading. And this is the three-dimensional wind speed. This 40 hertz data, and also the humidity. So using this data, so we can directly calculate the fluxes, the momentum flux and the humidity flux, and then we can actually, because we know the values of the fluxes, and then we know the surface wind and the sea surface temperature, and then we can backward calculate the exchange coefficients. So that's this result. So these are the data. So each point is actually 3 to 5 minutes flight lag. So and this is the drag coefficients from early experiments. This is based on the 8 field experiments in non-hurricane conditions. Some of them you may know, like Hexus experiments, the Showax, Sway, So you see the drag coefficients increases nearly linearly with the 10-meter wind speed. And actually, our data show that the drag coefficient actually tends to level off at a certain wind speed range. That's the findings from these observations. And we also look at the exchange coefficients for enthalpy transfer. And before our study, the exchange coefficients for enthalpy transfer for latent heat flux only goes up to 20 meters per second for surface winds. Those are based on buoys and ships observations. I mean, basically this CE is nearly constant, has no wind speed dependent, in the order of 1.1 times 10 to minus 3. And we found that actually this exchange coefficients for enthalpy transfer stay the same up to 30 meters per second. And also, I mentioned about this ratio, the CK over CD. That's an important parameter in this hurricane maximum intensity theory of Carey-Manuel. And actually, we check this ratio. Our observations show that this ratio actually can be smaller than 0.75. So this is actually smaller than the theoretical threshold. I mentioned about the unmanned aircraft. This is actually the unmanned aircraft. This is my colleague, Zhang. He's the leading PI. We got some, luckily thanks to Sandita Mandel report. So this is the toy. It's like a toy. This is actually the unmanned aircraft. So we dropped some of them in Hurricane Edward. And this is a new type, so we dropped it in Hurricane Maria. So you see, actually they let me to drop one. You see, that's me. Like the one I dropped failed. We dropped 6 of them, 4 worked, because this is the last one. I said, okay, maybe I can try one. Then I didn't work. So it still got some data, but not high frequency. It's like a drop sound. We got some data because the wing didn't span. So the airplane just went to the ocean, and then we got some data, like 10 minutes data. This is the unmanned aircraft data. So you see this is the first unmanned aircraft we dropped in Hurricane Maria. So we didn't control it much well, but we got some data at about 100 meter altitudes. You can see, oh yeah, here's the altitude, 100 to 150 meter, and we measured the temperature, humidity, and wind speeds. So we're still analyzing this type of data too. I mean, this type of data has a limitation in terms of the temporal resolution. It's kind of only 1 hertz, like 1 second data. So for flux calculations, there's some limitations. But again, this gives some, maybe give us some improved understanding of the structure in hurricanes. And then, I think I still have time. Next, I'm going to show you how we use this data to improve the hurricane models. So I have a paper published in 2012 talking about a developmental framework for improving hurricane model physics using observations. So this framework has 4 steps. The first step is to do model diagnostics against observations. So basically compare modeled hurricane structure to observed structure to see if we can identify some deficiency in terms of the hurricane model structure. And at the same time, we develop new physics using observations. I've shown you, for instance, we try to directly measure the fluxes to derive the new CD, CH parameterization coefficients using observations. I mean, this could be parallel, the first step. And then we put this observation-based physics into the model. And then at the end, we try to evaluate the impact of this input physics on the hurricane intensity, forecast, and the structure. So this is just an example. So we actually modified the CK exchange coefficients in HWRF. HWRF is the hurricane weather research forecast model. It's the regional model. This operational model has been used by the output by National Hurricane Center during real. Actually, this model gives the best intensity forecast. You know, ECM, WF, European model, or the GFS model. Those are global models. They are good for track forecast, but HWRF is good for intensity forecast. So back to 2011, we actually modified their exchange coefficients. You see in this pre-2010 version of HWRF, they use CK increases with the wind speed. Actually, our observations shows that the CK actually is nearly constant. So we modified that. I mean, there's also the House et al. Paper I was co-author. So this is based on wave tank experiments we did in University of Miami. Another thing, I mentioned about the model diagnostics. So this is how we look at compare the modeled mean structure. So I've shown you the observational composites from the drop zones, the inflow, outflow structure, and these are the boundary inflow layer structure from the HWRF back to 2011 version. So before 2011, the model has a resolution of 27 to 9 kilometer. So the innerst domain has the resolution of 9 kilometer. So every 9 kilometer you have great points. But we improved that. So we put a third nest so that the model has the 3 kilometer resolution. But you look at the structure compared to observations. So you look at this, the white line. This is the inflow layer depth. You see, back then in the HWRF model, so this forecasted inflow layer in the eyewall region is as high as about 3 kilometers. But in the observations, is in the order of 1 kilometer. So this, and also the model forecasted inflow is too weak compared to observations. So basically, we found this deficiency. We found the model couldn't reproduce this shallow inflow layer. So then why? Then we look at the model physics. We actually found that in the boundary scheme, the vertical eddy diffusivity is too large. I mean, compared to observations. So these gray dots here are from the HWRF before 2012 version. You see, I mean, those data were collected. I'm going to show you the data in the next slides. Actually, up to 60 meters per second. The eddy diffusivity is in the order of 100 meters square per second, but in the model, they use 500 meters square per second. So it's too large. So we reduced this value close to observations, not exactly as observations due to other reasons, track cost. So, and then we evaluate the impact of of this change of the model physics on hurricane intensity and the structure forecasts, and just show you the observations. So to derive the vertical diffusivity. This is an interesting storm. Actually, Bob, Danny, we talked about this yesterday. This is actually the Hurricane Hugo flights. This is the famous flights back to 1989. This is a Category 5 storm. Actually, back to those days, the pilots were really brave. They flew P3 at 500 meters, eye wall penetration. You know, the data I showed you for my PhD work, we flew the airplane to 60 meters, but in outer core at 100 kilometer away. But in this storm, they flew at, the really high wind region. You see sorry for the vertical scale, but you look at this is the flight level data reached to 80 meters per second. So the vertical velocity, you see just within one minute, just go from minus 10 meters per second to 20 meters per second updraft, from a downdraft to updraft, even within 2 to 3 minutes or the 10 seconds. Actually, they had almost had incidents during these flights. They have the fuel inside the eye because of the turbulence. So they stayed in the eye for like 1 hour, climbing slowly, dumping the fuel and then fly out. So this is the most scary hurricane flight, I think. So I used I went back to those old data. Actually was stored in the storage room. I found the old tapes to process the data. I think this data is pretty useful. This is actually the only data of this kind for the boundary layer research, because this is at 500 meters. So I was able to calculate the fluxes using this data, and also derive the vertical eddy diffusivity. Those points are from the Hugo flights, actually, the highest wind speed, the ranges. So we actually use this data to improve the hurricane model physics. And just quickly show you the impact of how this model physics change would affect the intensity forecast. So this is what we usually do. We modify the model, and then after we modify the model, we'll rerun hundreds of cases. We run all the storms of the past 2 to 3 years to get the statistics in terms of the track error, and this is the absolute track error, absolute intensity error. So we compare the two versions of the model. You see, the red curve is after the modification of the physics, and this blue curve shows the error before the modification. You can see that. EMC, the Environmental Prediction Center, they run 37 storms. You can see for both track intensity, we see 10 to 15% reduction in terms of the error. So actually, improving the model physics helped improve the hurricane model's capability for hurricane intensity and track forecasts. And also, I mentioned about the structure. So going back to the boundary structure, and so here, left-hand side is the RZ mean, radius height, plots of axisymmetric tangential wind on the left, the radial winds on the right. So here, the upper panel shows the structure, model structure before the modification. This is a 3 kilometer resolution. You see the inflow depth is about 2 kilometers, and this is after the modification. You see the inflow layer depth is reduced to about 1.2, 1.5 kilometers. It's much closer to observations. So basically, by changing the model physics, not only improve the hurricane intensity forecast, but also the structure. So, this is the last slide. Basically, this is a case study in this. So those figures are actually a composite of 120 H4 forecasts of 4 storms. So basically, this is a composite of the model run compared to the composites of drop zones, of 800 drop zones. So in the case study, we also look at the boundary recovery process and also other physical processes. This is an example what I did recently. Compared 2 H4 forecasts of Hurricane Earl 2010. You see this red curve here is the intensity time series for the low cam, the modified physics forecast, and this blue curve is the intensity time series for the unmodified physics run, and this black line is the best track. So we select the case in which our physics modification made a really good forecast, and then we look at the structure. So this left-hand side two figures show the theta E, the enthalpy. I showed that for observations at a 100-meter altitude for high Km forecast on the left and low Km forecast on the right. And here, this arrow here, the shear, the environmental shear direction, the large-scale shear. And you can see this, again, on this up shear left quadrants, you see this low theta air in both H4 forecasts. But you can see that when we reduce the vertical diffusivity, actually the theta E is increased. You know, in this run, although in the up shear left quadrants, it's still smaller than the down shear right quadrants. And this is the green line shows the trajectory of basically the air parcel would rotate from the air up shear left to down shear right quadrants in the eye wall. So I did the estimates to see if surface enthalpy fluxes are enough to recover this, again, this theta E deficit. Actually, in this high Km run, the surface fluxes are not enough to recover this the low theta E air from the up shear left to down shear right quadrant. But in this low Km forecast, the result is opposite. Actually, the fluxes are enough to recover this theta deficit. So basically, when we modify the hurricane model physics, that also influence not only the kinematic structure I showed in the previous slide, but also the thermodynamic structure. Here we only modify the vertical turbulent mixing of momentum. So actually that affects even the thermodynamic structure. So that's it. I will just quickly summarize. So we use GPS drop sound data to study the mean boundary layer structure in hurricanes, and we try to directly measure turbulent fluxes so that we could derive the exchange coefficients for momentum and enthalpy transfer. We also calculate eddy diffusivity based on observations, and then we use these observations to model evaluation in terms of the structure. We also use these observations to improve the hurricane model physics, and this observation-based model physics improvements actually led to improvement of hurricane intensity in the structure. So that's it. Thank you so much.